Okay, welcome everybody. Welcome to all the online viewers as well to the second joint astronomical colloquium of the current semester. We're going to continue today with the theme of radio astronomy, and even with the theme of low-far radio astronomy, started last week in the distant universe, but now we're going to the relatively local universe, and we're very pleased indeed to have Joe Callingham, head of the SK Science Group, ASTRON, to tell us a little bit about this. Before I pass over to Joe, I'd like to just to go through his already very distinguished career. Actually, I think it's probably true to say you were a student of Brian Getzner and Ron Eakers in Sydney. Yep. So in a way, you are carrying on this long tradition of Australian radio astronomers who've come and really made big impact to the field also in Europe and the USA. Joe did his PhD, graduating in 2017, and then I think you just went straight to Leiden, and you've been there in several positions ever since. One thing to point out that you were in 2024 recipient of an ERC starting grant. And the year before, you were made, I think, the representative of the SKA working group in the Netherlands. So that indeed is a really distinguished role, given the history of the Netherlands in radio astronomy. During this time in Leiden, you've done a lot of research and a lot of observational research, not just in radio astronomy, but also multi-wavelengths. And what stands out, I think, is that you were the first person to really take a systematic study of the radio emission from stars, doing blind surveys. And in the course of this research, Joe actually made a few discoveries. And what really, to me at least, is really outstanding and interesting and unsurprising is the potential detection of emission from essentially planets, or at least planetary stellar systems. And I believe that's the main topic of your colloquium today. So thank you very much for coming in here. We very much look forward to hearing all about this exciting new work. Thank you.
Thank you. I appreciate it. Everyone okay? Hear me fine? Yes. Thank you again, Richard, for hosting me and spending your time here. It's a pleasure to be at Heidelberg. This is my first time ever to Heidelberg, and it's kind of a mecca of astronomy. And so it's a pleasure to be here and presenting my work. As Richard said, my name's Joe Callingham. I'm based at ASTRON. For people unfamiliar with that phrase, it's kind of like a Max Planck Institute of the Netherlands, which is focused on radio astronomy. So equivalent to the MPIFR, if you've heard about that, located in Bonn. And I'm also an assistant professor at Leiden. So I'm going to give you a talk today about radio stars and exoplanets. And so you've probably heard of stars and exoplanets, I hope. And most often you don't often hear from this in a parameter space of radio. And I'll convince you why this is interesting and why we should care in this parameter space. Now, we're a small enough group, I hope to make this somewhat interactive. So if you've got a question, don't keep it. You can interrupt as I go, and I'm happy to repeat it for people online. So don't let it just rot in your head. Just shoot your hand up, and I'm happy to take it as we go. There's no point in me presenting stuff if you're just sitting there and not understanding. Okay, so let's get underway. Before I go on, I think any good scientist should recognize this is not done in isolation. The only reason I can present half this work is because I'm embedded in a fantastic team. And in particular, I just want to acknowledge Harish Vendetta and Tim Shimwell at ASTRON, who have just been fundamental to building this. Same with Ben Pope at UQ, about to move to University of Queensland, for people unfamiliar, is about to move to Macquarie University in Sydney, and Cyril and Tass and Philippe Zarka and CNRS. Without these guys, I wouldn't be able to present this stuff. So let's get away with a little bit of fun, get started with a bit of fun. Now, what I'm showing you here is just the electromagnetic spectrum to make it a little bit more fun. This is sea creatures. This is kind of what you look online. We all know what this is. It's just kind of give you a physical scale. And with radio astronomy, we at least get this nice parameter space where we're talking about physical scales that are appreciable. I was talking to a lot of gamma ray astronomers. If people care about gamma ray astronomers, you're stuck in talking about like DNA and stuff like that in terms of wavelength structure, but we'll get into other things as we go. But before I start, I just wanted to ask a very simple question. What do people think the brightest object in the sky is at X-rays and gamma rays? Anyone want to guess? This is probably true for X-rays. Now I feel like I'm talking to gamma ray astronomers. I have to be careful. Anyone want to guess? Don't be shy. It's the sun. Yes. At X-ray and wavelengths, the sun's right next to us. It's super bright, and it's the brightest things at those frequencies. Oh, sorry, my computer's taken off. Now, what about at infrared or optical? It's not a trick question. It is also the sun, right? The answer is the sun. But something really interesting happens at around 40 megahertz, some of these really low frequencies. And something starts to be brighter. Does anyone want to guess what that could be? Obviously, the answer is not a sun because I just gave it away. It is Jupiter, yes. So actually, the crown of the sun is stolen, usurped by Jupiter at 40 megahertz at radio frequencies. It's the only wavelength in the entire part of the sky where Jupiter outshines our own sun. And this has got to do with a particular type of emission mechanism that does this. Now, and I'll come to discuss in this section. And so the premise of my talk is, can we find other Jupiters out there on this radio emission? And that's pretty much the rest of my talk. And it tells you something about the magnetic field. So maybe let's just put this in more of a scientific framework instead of great white sharks and pygmy seahorses. What I'm showing you here is flux density on the y-axis, frequency on the x-axis, a radio SED it's called, or a radio spectrum. And all I've done is plot some of the brightest radio sources in the sky. Things called Cygnus A, which is a giant radio galaxy, the Crab Nebula, which is a pulsar wind nebula, and you've got the Quiet Sun. And you also got Cassia, which is a supernova remnant. And you see how bright these are, but at around 40 megahertz, you can see this big whopping bright thing pop in, and this is Jupiter in the black. And I'm just showing two different types of activity cycles, one where it's bursting a bit more and one that's more, you call it quiescent emission. It's complicated terminology, but you can see it's a pretty weird spectrum. It cuts off quite dramatically. Again, this is due to the emission mechanism. But what's interesting, if you just want to take something physical from this, if you can measure this cutoff where you detect and don't detect the star, this directly tells you the strength of the magnetic field on Jupiter. So Jupiter's got a roughly 13 Gauss field, and the equation goes 2.8 times B, and that's more or less what you get, 40 megahertz back out. So this is what we're trying to chase. And why are we trying to trace this? What information could be important? Let's put this in a better scientific narrative. I probably don't need to tell you because you've got MPIA just around the corner, but we live in this time of astronomy now where I probably wouldn't say it's easy, but it's becoming standard to find planets around other stars. If you really want to know if there's a planet around another star, we now have the radial velocity instruments, or if you get lucky on transits, of being able to answer that question. And you can see the complete menagerie of stellar systems we're identifying. Don't get me wrong, we have huge biases right now in our search algorithms. We're biased to, obviously, massive planets close in, both RVs and transits, the workhorses of exoplanet discovery are biased to that. And you can see our solar system overponded. We haven't found a solar system analog because that would take decades of monitoring to be able to confirm that. And also, what's happening now is not only are we finding exoplanets, a lot of effort is trying to find planets around, what are these called? These M dwarfs. These are stars about 10% the mass of our sun, or roughly 10 times the mass of Jupiter, as rough numbers. And the reason why we care about these is essentially threefold. One, they're the most prevalent planets in the universe. About 80% of all stars are M dwarfs. And so that means if you're hunting for, say, an Earth-like planet, you don't want to ignore potentially 80% of all hosts. And so you really want to do that. Number two is more of a dumb and basic reason. It's the reason is because they're so small, they're heavily influenced gravitationally by another body, much more than the sun. So if you put an Earth next to it, that's great. And the third reason, because they're small, they have that kind of standard Goldilocks zone is much closer, which means you don't need to monitor, say, for 3 years a G-dwarf. You can only monitor for tens of days, and you can get the same kind of, enter the same parameter space, what's called sometimes the Goldilocks zone, if we're talking to the public, or what I call, and many people call, it's not just me, the conventional habitable zone. The idea that with an M-dwarf, now that habitable zone which Earth sits into, which is roughly an AU, is now shrunk within the orbit of Mercury. Now, this is kind of where exoplanet astronomy now is really trying to explore. It's like, great, we're in this parameter space that potentially we can find planets in what's called this conventional habitable zone, but we have this issue of like, is it really habitable? this idea of the conventional habitable zone has to change. And why does it have to change? Because we know, even in our own solar system, that sometimes our sun isn't even a good host, right? It has these massive eruptions in the corona called coronal mass that cause superheated plasma to spill out and impact to the Earth. But luckily, we're at an AU, right? So that energy and heat dissipates over an AU. Also, the chance interaction is substantially lower because you've just got a larger cross section. But now I've shrunk this within an orbit that's smaller than Mercury. Not only if a CME goes off, the planet's right there, but also it's going to be much more likely to interact. So how often do these coronal mass ejections occur on other stars? We actually don't know. We've never really convincingly, and I'll come to touch on this in a second, guaranteed that mass has been ejected from another star. We've seen massive flares, but we never convincingly can say that mass has been ejected. And the other one is a huge unknown in this parameter space, is that we know from the Earth-Sun system, and this is controversial, but again, happy to take questions on it, is that we think our magnetic field kind of acts as a shield in the faces of this type of activity, the stellar onslaught. So what you're seeing here is a simulation, and a coronal mass ejection is coming in red, and that's just density. The gradient's just density. And you can see the magnetosphere of Earth, just the magnetic field entrapping this stuff. And this is actually called the Carrington event, which happened in 1852, 59. Anyone remember in the audience? 1850s, so let's just say. And if you've got a long enough memory, this like caused aurora to go down to the equator and wiped out the telegraph network in Europe and North America. It was quite a dramatic event. But we think the Earth's magnetic field is fundamental to making sure our atmosphere doesn't get stripped in the face of this pressure, in the face of this onslaught. So I've described kind of two parameter spaces that we're beginning to explore habitability from. There's lots of different other ones, obviously. This is a complex, multifaceted problem, but we're going to focus on these two right now. What I call the unknown space weather conditions that other planets around other stars experience. And the first one that we really need to get a handle on is how often does a CME occur on a star that's not our sun? And what kind of energetics does it have? They're just so unconstrained. Just to believe, like, we take the sun, which is a single star at a single mass at a single point in its life, and we just extrapolate. That's all we're doing right now in a lot of literature. While an M dwarf has a dramatically different magnetosphere. It's got kilogauss fields as opposed to a Gauss field. And it's got much more complicated topology in a lot of cases, or more simple topology. You've got a whole menagerie of things. So this is heavily unconstrained. And the other one is we've never directly measured the magnetic field of an exoplanet. And we know from our own solar system, there's a piano in here? Anyway, got distracted. Our own solar system, that this is just wild how much it varies. Like Venus doesn't have a magnetic field, even though it's roughly the size of Earth. Mars doesn't have a magnetic field. Jupiter has a very strong one. Uranus is tilted and weaker than you'd expect from first principle. Dynamo theory here is really a tough theory. And so maybe we can help from the observational side by providing different evidence here. So these are the two answers I'm going to focus on today. And this is obviously biased. You know, you talk to another exoplanet astronomer, they'll say like atmospheres are the most important thing to measure first, all this kind of stuff. And the other reason I'm focusing on these, and I'm just going to be honest here, is I'm a radio astronomer. So radio astronomy can help in this parameter space. But there's lots of other things to tackle. So the first one is like, how can radio help? Is that accompanying all fast coronal mass ejections from our sun is you have what's called a type 2 burst. And what I'm showing you here now is on the y-axis frequency, on the x-axis time, and in the middle here, sorry, people online, it's got a label right next to it. It's called what's a type 2 burst. And this type 2 burst has a characteristic sweep to it. And this encodes the kinematic of the burst. It tells you how the number density is changing with distance, particularly if you can measure the magnetic field of the star. You can then back out the velocity of the shock, and you can also back out the number density, because this is called plasma emission. So the frequency emission here is just related to the square root of the electron density. So that's fantastic. If you can measure, if you see a type 2 burst on another star, you can pretty much convincingly say there's been a coronal mass ejection. This is important because I've already alluded to it. We know M dwarfs flare. So in the top right-hand corner, I'm just showing you a TESS flare. This is an optical flare for anyone that doesn't know what TESS is. On the y-axis is flux, on the x-axis is time. And just look, it went from This flare is just gigantic. M dwarfs are known to go off all the time. This got to 15 times larger than its ambient flux level. That's a huge impulsive event. But we have no idea, even though this huge impulsive event happened, we have no idea if that actually represents mass being ejected in the system. You know there's a magnetic reconnection event probably happening, but because they have such strong magnetic fields, you could just retrain that matter, just keep it within the magnetosphere of the star. So even though you have giant flares, and which put out a lot of UV, so probably not ideal for a planet around it, because UV is just going to escape independent of the magnetic field. The more important thing is, what is the particle impact on the planet? And you just don't know from this. And so this is why we're chasing these type 2 bursts, because that means, if anyone's a plasma physicist or an expert in plasma physics, a super alphanic shock is formed. So you had causal disconnect of the mass from the magnetosphere of the star. So that's the first one. And the second one is more attractive to the eye. Aurora. Did it make it all the way down to Heidelberg? Could you see it recently? There was some really bright aurora in the Netherlands. It probably didn't make it all the way down to Heidelberg. It's probably just too far south. Well, you can stand on mountains here as opposed to the Netherlands, so maybe you get lucky. In the Netherlands, you're like, okay, just don't be a big tree in the way. And so these beautiful aurorae, which are generated by the impact of some of these coronal mass ejections hitting the magnetosphere of a planet, actually, you know, they look beautiful to our eyes, but as I already alluded to Jupiter, if I could turn your eyes into radio receivers, this is some of the brightest things you'll ever be able to see. This is terrible. You don't want aurora happening when I turn on my radio telescope. It just makes life very, very grim in terms of trying to do science. So what kind of aurora are there that you want to chase in the radio? There are obviously optical signatures, but they're very slight. Maybe the TMTs and the GMTs and the other large optical telescopes in next generation could chase them down with some complicated spectroscopy because you get particular lines. But I'm just going to focus on what's called radio aurora. And this is the classic one. This is the one you're probably familiar with. This is when you go to Iceland or you go to Norway or you go to, if you're lucky enough, Antarctica. I have to always remember my southern hemisphere friends. You know, when you chase aurora borealis or aurora australis, you're essentially doing this. You hope that you have an active sun that impacts the magnetosphere of the Earth. You have a reconnection event in the tail, and that drives the aurora at the poles. And this aurora is just what you see on Jupiter. You can calculate the magnetic field of the planet itself. Now, that's one type of aurora that you could hope for. The other type is a little bit more sophisticated, but not much. It's just called a star-planet interaction. Now, if you have a planet next to a star, what it does is actually perturb the magnetic field of the star. And this can drive aurora back onto the host body. And this is a conductor. What is this modeled of? How can we be confident on this? It's because this is what we see on Jupiter. You can play the thought experiment. Would we predict this from first principles? You can, based on the plasma physics, but would we believe it if we didn't have Jupiter and Io? It's an interesting question. What I'm showing you here now is what's called UV aurora, which is a tracer. If I showed you the radio, we can't localize as much. You've got the auroral oval here, which is kind of similar to this, a little bit more complicated. If you want to know the details again, ask me afterwards. I don't want to waste time explaining the intricacies of the auroral oval, but you might notice this hot spot and curve. This is actually what's called the Jupiter-Io interaction. Io, lots of volcanoes, very volcanically active, and it's actually a conductor. So it's spilling plasma into a torus around Jupiter, and as it moves, well, really I should say as Jupiter, because Jupiter's spinning at like 12 hours, it's going very, very, very fast. As that magnetic field sweeps over Io, it actually perturbs the magnetic field and sets up a current. This is essentially year 12 physics. This is just Lenz's law to some large extent. You just have a magnetic field bearing over a conductor that sets up a circuit and drives the aurora. The only thing that's fancy on top of this is the plasma physics to get some population inversion going on at the poles. But the details aren't important. It's just that if you have a perturbing body, you can generate radio emission, and that tells you something about the planet that's perturbing and also the magnetic field strength of the host body. In this case, the host is Jupiter. In this case, what you do is you replace Jupiter with a star and Io with an exoplanet. And then maybe you can find it. And that is the premise of the idea that my colleagues and I about 2024? I'm getting older. About 5-6 years ago had. Well, because the problem is, even if I put Jupiter at a few parsecs, our most sensitive radio telescopes just can't see it. Even though it's whoppingly bright, we're just lucky it's next door. So how do we boost the emission? How can you make it more luminous to try and get more energy out, more radio luminosity? And one way is by doing this. You just amp up the mass. You make this a larger obstacle. So you make this, instead of Io being a little moon, you can put Earth there. And instead of Jupiter being a planet, we can put a star there. And if you do the back of the envelope calculations, particularly led by Zaka and those in the early 2000s, you're like, well, maybe you could see these things, but there's a lot of unknowns. And so that's what we set off to do. And so we needed a sense of instrument, and that's instrument. I heard Leia Morabito was here last week, so you really have had LOFAR. You're probably sick of hearing about this ugly telescope in the middle of nowhere. It's not much to look at. It's only about yay high, it goes up to your knee. But if I could show you what's under these tarps, are just lots and lots of fancy coat hangers. Very expensive, but they're essentially just fancy coat hangers. And what makes LOFAR special for this science, there's just lots of them. So I can operate at very low frequencies. I should have mentioned that earlier. All these signatures are at low frequencies. As you know from the cutoff on Jupiter, right? If you scale that, you really kind of, if you want to find Jupiter analogs, you're stuck at low frequencies. And so that's why you want to do it at this space. But this is hard. This becomes, oh no, I feel like people are losing it. I don't want to go lecturer mode. But the reason why it's hard is because we become, at some level, optical astronomers now. The benefit of looking at a gigahertz, you know, kind of like what your phone works on, right? Like the photon just passes through brick. It hardly gets impacted by its path. But if I go to low frequencies now, the ionosphere disturbs us, just like similar to seeing disturbs us. And so you have to correct for this. And this is tough and hard. And that's why it's taken to essentially the 2010s before we really started attempting this, as opposed to, say, the VLA or the compact array or others you hear. So maybe I'll just give a visual impact of why LOFAR is so fantastic, just so you can resonate. So this is called NVSS. It's a background image for the galaxy people in the audience or online. I hope you're probably familiar with this, particularly if you're a radio astronomer. This is just an all-sky survey by the VLA, done in the late 80s, early 90s. And I would say it's a gold standard of all-sky wide field surveys. And what you see here, all these black dots, are mostly just AGN. And you might notice some are partially resolved. And you see about 50 sources per square degree. Another kind of gold standard is what's called FIRST. This was also done by the VLA, but it's interferometer, so they just did a different configuration. You can see it has higher resolution, but if I flick between the two, you can kind of see you've lost that diffuse structure. So this is what's called a head-tail galaxy because it's near a cluster. And you can see that kind of resolves out, and you're left with just the point source right at the top there. All that diffuse stuff is lost because the interferometer is kind of like a net. Depending where you put the antennas, depends what spatial scales you're sensitive to. So that's what it looks like for the gold standards. What does it look like in our all-sky survey? So just that, for that, for that. So you can see now we're recovering all this scale. And the most important thing for this science to take away is this number here. Instead of 50 sources per square degree, now we're at 750 sources per square degree. We're just surveying the sky at a much deeper depth. And on top of that, at low frequencies. And we're doing it with short baselines and long baselines so you can recover all this large-scale structure, which is quite exciting. So where are we sitting? And maybe this is, if you're in the audience, you're like, oh man, this is a bit boring, stars and planets. We're nearly finished with the full survey of the northern sky. Now, this slide's even old. I tried and update it, but the plotting script died on me, so it's nearly a year old. We're essentially going to release by, I'd say, mid-next year, the entire northern sky, excluding the galactic plane. So if you've got a favorite, and 10 degrees of the galactic plane. If you've got a favorite source, even now, there's 90% certain I've got it covered. Just come and talk to me or send me the coordinates so I can look it up. If you want to know what it looks like at 144 megahertz, I'm very happy to do so. We've also got some galactic fields covered, but this is just tougher. Galactic, as you know, interferometry requires a lot of image reconstruction. And when you go to the galactic plane, you've got lots of different scales. When you do extragalactic fields, it's usually much simpler. So anyway, that's just a spruik for lots. And if you've got a favorite source and you want to know what it looks like at radio, I'm very happy to have a look for you. Okay, so to set the field, remind us where we are. We want to find stars out there because they may be doing coronal mass ejections or maybe star-planet interactions. And how do we do that? How do we begin to do this when if you look back here, I can tell you with confidence almost 99.9% of all these sources in the sky are extragalactic, particularly when you're off the plane, right? These are just a quasar at redshift 1, a quasar at redshift 1, a quasar at redshift 2, so on and so forth. So how do you pick out these star-planet interactions? And it's a little tough because the problem is like you take Gaia, which has billions of sources, right? And you throw that at the board, and then I take LOTS and I throw that at the board, but LOTS only at the LOFAR survey only has an astrometric accuracy of 0.2 to 0.5 arc seconds. So the chances of an M dwarf just sitting on top of a redshift 1 quasar is actually quite high. It's very annoyingly high. So you have to do something more sophisticated. And the thing what we did that was different is that we went to circular polarization. It's because that aurora and coronal mass ejections, they all have a very distinct signature in the fact they're circularly polarized. This is again got to do with the plasma emission characteristics. And so it's because it's what's called a coherent emission mechanism. And so that has essentially kills all your false positives because it gets rid of the AGN. All the AGN are 1% or less, majority much less, circularly polarized. It's just synchrotron emission from many different electrons, many different field orientations. And so it averages out to essentially 0. And so that's the way we found it. So to give you an idea of what this looks like, this is our first detection of a star. On the left is one epoch in June. On the right, another epoch. You can see by the dates, 2014. We only published in 2020. That's how hard the data challenge is. Just to give background, I'm sure Leia probably set this up last week if you saw this. It's not a simple problem doing in terms of data rates. It's enormous. You know, this data cell by itself fully reduced is about 20 terabytes. And so just we have to do that thousands of times over the field, and that's the reduced data. When it's not reduced, we're talking about petabytes of data. Anyway, so how do I know it's a star? Well, the first one is this is one epoch and another epoch. So luckily, with stars and exoplanets, you expect time variability. So that's one way to identify it. You know, it should turn on and off. And the other one is an inset. This inset is actually the circular polarization. It's the same size of the image. And you can see, maybe you can see these background other sources, these AGN at redshift 1 have all disappeared in the inset. And that's because they're not circularly polarized. And that's how we could be confident that was our first detection. And we did a whole bunch of physics, which I'll touch on in a second about this. And so what are we sitting at now? So we've analyzed about 25% of the northern sky. And I always feel weird as a radio astronomer presenting a Hertzsprung-Russell diagram. I don't, like, if you ask me in my PhD, which is on AGN, whether I'd ever show a Hertzsprung-Russell diagram scientifically. Yeah, but here we are. So what I've got is absolute magnitude against Gaia color on the x-axis and absolute magnitude on the y-axis. The blue is just the background Gaia population to give you an idea to trace your eye. And in the colors are the detected stars we've had. So you can see we almost fully sampled the full sequence of M dwarfs. So we've got early type M dwarfs and late M dwarfs. That was unexpected. But based on VLA and the compact array stuff, they expected this to be dominated by late types. You kind of see like brown dwarfs or late types. They tend to be more magnetically active than early types, but we just see the whole spectrum. And we also, you might notice, we're sampling a lot of this kind of instability strip of the HR diagram, the giant branches and so on. These are called RSCVN. Oh, I can't remember the spelling. Anyway, I'm not going to butcher it. RSCVN BY DRA. They're chromospherically active stars. These stars have magnetic giant spots. Like 45% of the disk is covered by a spot, and they are interacting with one another. And so they are also very bright in visibility. We've got this weird guy down here. I always like quizzing people what they think it might be, but the answer's on. Is there any radio astronomers that recognize what an MSP is? Does anyone know what this is? Besides Richard, he's a glorified radio astronomer. Well, anyone want to guess? You have to say it louder. You know, there's no wrong answer. A millisecond pulsar. So what we're seeing in the radio is the pulsar, and in the optical we're seeing the companion, because all millisecond pulsars are binary. So they're accreting mass, and that's why they spin up to a millisecond. So you can see we're sampling this kind of stuff, and this is only 25% of the sky. By the end, if you do some source counts and some guesses, I estimate about 300 plus or minus 100 detections by the time we finish the survey. I think that's going to be I think that's probably over generous now, because from memory, I think I included the galactic plane in that estimate. So you can tell me how wrong I am in a couple years. Another interesting one here, you can kind of see we have some of these unknowns. They're a bit hard to see. They're in the black triangles. These aren't really stereotypical. For example, we've got this isolated F5 dwarf. It's the only non-M dwarf and it's not chromospherically active. It looks incredibly boring. It's not X-ray bright. It doesn't have any of the activity indicators you expect from stellar emission or stellar activity. So what's going on there is a good question. We haven't solved that one. I think it's probably going to be, the answer is it's got an M dwarf companion, but who knows? So why is this interesting? Well, essentially, there's only three things. I'm sorry, I hope I'm not losing people. Lots of plots. There's about only three known things that are bright in the radio sky that's circularly polarized. One, stars. Whether that's star-planet interactions, CMEs, you have to do later, but stars are one. Number two, pulsars. They also have a coherent emission mechanism. And number three, brown dwarfs. And what's nice is if you can measure the circularly polarized fraction, you can begin to say what you think these things are. And that's useful because if you find things you don't have companions, then you can start isolating them. So what I'm showing you here on the y-axis is circularly polarized fraction. Stokes V on Stokes I, people familiar with the terminology. And on the x-axis, I've just got signal noise in Stokes I and Stokes V. So let's just focus on Stokes I. What you can see in the yellow is pulsars. And the yellows are known pulsars. You can see pretty much a majority of them are bumping around the few percent to 10% level. And most are probably even less than that. It's just that I can't detect them in circular polarization. But you notice there's three black triangles there. They weren't known things. And lo and behold, when we went and followed up at timing, you find the new pulsars. And you can see most of the stars sit at much higher circular polarization fraction. But you also might notice two new kind of black triangles. They don't have a Gaia counterpart. They don't have an optical counterpart. So what could they be? They're most likely new brown dwarfs. Because Gaia is quite complete to nearby things up to M4. Anything later than that has to become a late type M dwarf further away. And actually, we've got Gemini time and confirmed them to be new, very cool low mass M dwarfs like T4, T5 for people interested in brown dwarfs. So what's causing this emission? Particularly what we do in a lot of our papers, we go through a kind of a theory component of looking at the quiescent M dwarfs. So the important thing to take away from here on this previous slide, this M dwarf sample kind of splits into two branches. One, we see the M dwarfs you expect, the active bully things, the AD Leos, the UV Cetis, the UQ Pegs. We find those as well. But then we also find these other stars like GJ 1151. If you said point blank to me what kind of stars you expect to find 5 years ago, I would never have said a quiescent, boring M dwarf that doesn't look to be active in any other domain. It's not X-ray bright. It doesn't flare regularly. It hasn't got H alpha that's very bright. So what could be driving this emission in the radio? And you kind of get cornered. It's very hard to explain in plasma emission. And so we proposed that these can be explained in a signpost method of just a star-planet interaction driving this. And this is what's called electron-cyclotron maser instability driving this emission. And it's the aurora that we said. So if you make that statement and you do that theory, you make predictions. And the prediction we make is that we expect, this is just now flux against distance for a putative planet around this star, we expect an Earth-like planet in a roughly 1 to 5 day period can generate the radio emission you detect in terms of the luminosity, in terms of the spectrum, in terms of the time variability. And so we made a prediction. Now we go to our optical colleagues who are RVs and go, is there a planet there? Can you find one? And the answer has recently, and this is now very hot off the press and not published yet, is that we're beginning to find the planets around some of these stars as we expected it. So this is a 1.2 day period Earth-like planet around one of our stars that we've detected. So that's incredibly excited. But again, this is not really proof, right? It's just supporting evidence thereof of this inference. All this argument I provided you so far that these are star-planet interactions is inference-based in terms of an ideology. What would be the smoking gun here is what's called, if we saw periodicity in the radio. So what I'm showing you now is a simulation of radio against time. And what happens is this should just turn on and off, just like a lighthouse, on the orbit of the planet. Now we know what the ephemeris of the planets are from our optical colleagues. We can target particular phases of this to try and nail to see if it turns on and off exactly as we expect. And this is just a simulation. And so that's what we're working really hard to do. The problem is LOFAR just turned off for a massive upgrade and won't turn back on to the next year. So we're kind of in a holding mode, but this is kind of, if you put it in, if you had to set my arguments in line here of this star-planet interaction, I would say we've got good inference-based evidence that we're seeing star-planet interactions, but we haven't got the smoking gun. And the smoking gun is going to be this. And it's tied to what the RV people tell us. Obviously, we'd love it if it transits, but only, what's the number? 1% of all planets transit the star, or 0.1%. I can't remember the quite order and magnitude of it. Does that make sense? All right. Now, maybe just to move on and try and activate other people, because I know I've got a broad audience and I'm going to cover a little bit more different science territory now. And hopefully I know there's white dwarf people in the audience and all types of stuff. I just did one of the deepest surveys in circular polarization of the radio sky. Well, have we found anything interesting? Is there anything else we could pick out that might tell us something about the universe? So the first one is hot off the press, and I really do think we've probably got the first type 2 burst from another star. And so this is it here. I'm just writing it up now, so you can see, obviously it's not as high signal noise as our sun. This is a 40 parsec M dwarf, and we've got a characteristic sweep. And you also potentially, for people that are experts on type 2 bursts, maybe you could say, maybe there's band splitting, maybe there's some herringbone structure. It's a bit hard to be able to say because obviously we're signal noise limit, but this is how a new field starts. You kind of start with a ratty data and hope you get better. But if you do the sweep, that drift corresponds exactly to a shock velocity of about 1,400 kilometers a second. This is all kind of being consistent with solar. And based on how many M dwarfs are sampled for how long, and to try and find this, it roughly works at solar rate. We'd expect to detect about one of these in our survey so far, and we've got roughly one. Obviously, there's a huge Pearsonian rate error on that, but this is something I'm just writing up now. And if I have any moment, I will finally finish that paper. Been sitting on this a bit too long. So that's very exciting, and hopefully I'm right, but I have no idea really, to be honest. Anyway, so the next one, we've been chasing other stars. We're seeing all types of these dynamic spectra. I should have explained on the previous one. Again, frequency against time, brightness coming through on the y-axis. Oh, sorry, that was exciting. And you're seeing different types of bursts from all types of stuff that are quite hard to explain first principles, very complicated structures in these. These aren't type 2 bursts. These aren't solar-like. The M dwarfs are clearly doing something differently. This is actually done with a compact array. The reason we did this is because LOFAR is stationary, so we had to go and do something else. So Sana, one of my PhD students, she got 250 hours and just monitored and tried to see if we could see periodicity on AU-MIC. For people unfamiliar with AU-MIC, this is just an M dwarf that has nearby planets. So we know a priori there's already planets on there. So that's what we went hunting. And the answer is we did see periodicity, which is nice. This is the Loam-Scargile periodogram. People unfamiliar with this is kind of a fancy Fourier transform of the light curve. And this is the light curve folded to the rotation rate of the star. And you see lovely signal sitting, unfortunately, right at the rotation rate of the star. Not at any planetary period, as we were hoping. But this still tells us that the emission mechanism of Jupiter can definitely happen on M dwarfs, because Jupiter's auroral oval, that is totally governed by the rotation of the planet itself. And so we are seeing this type of emission on the other stars. We're still hunting for this star-planet signature. And just to give you some physics here, we played around with a toy model of auroral stuff. It's just you have so many parameters. And maybe what do you go from here? If you're maybe not a radio astronomy audience, probably won't appreciate this. But remember, I just told you we're using LOFAR, but I didn't tell you the exact frequency. We're using it at 144 megahertz. That means we'll never see Jupiter, no matter how long we integrate. We need to go below that. The problem is you go lower and lower frequency, the ionosphere becomes much, much more tough. Kind of equivalent to go to infrared. As you get higher and higher infrared, the atmosphere becomes very complicated and you get stuck. And then you essentially have to go to space. We're doing the same thing. We're going to lower and lower frequencies, but that causes lots of grief. But we're conquering. This is Christina and another PhD student, Christian Groeneveld. They're making images now. And this is a part of the electromagnetic spectrum that really hasn't been explored at all. In the early days of radio astronomy, they made 1 or 2 measurements. Now we're going 2 orders of magnitude deeper and with higher resolution. So discovery space potential, definitely, because every single time an astronomer opens a new electromagnetic part of the electromagnetic spectrum, you find something different. But it looks garbage probably to your eyes, but it's just amazing this is being done now at 20 megahertz, and we can go down to about 10 megahertz. And to give you maybe what would be more impressive to optical astronomers, just look at the y-axis and the x-axis, right? This is 10 degrees. One snapshot of LOFAR at these low frequencies does 10 degrees in an hour in RA. And so you just can survey the sky super quickly. You just go through them and measure everything. And it doesn't take you years and years and years. And so what kind of weird things are we potentially finding? Maybe this will be interesting to the white dwarf people. So there's this new class of objects. I'm kind of covering lots of range now. Hope the thesis will at least follow through, which is circularly polarized things. There's this new class of objects that's becoming quite fashionable in radio astronomy called long period radio transients, or ultra long period transients. Obviously, you can see by the name, by definition, that they're phenomena that's being found by observers, not a priori predicted by theorists, because the name's a phenomena. What we're seeing is things that are very, very bright, unexpectedly bright, but only for a shorter period. So 100 millijanskis. If you ask me a priori, do we understand the sky at greater than 100 millijanskis? I would have said yes. That sensitivity has been surveys. We've done wide field surveys. But these things are only on for about 10 seconds. And they've got long periods. Some are on minutes and others are up to hours long. So that's a bit odd because a pulsar can't do that. Pulsar is rotationally powered. And so when you get that long, you essentially just don't have the energy to be radio bright anymore. So what are some of the ideas? What could be causing this? And so I'm just showing the quite stochastic bursts. They're still periodic, but you can see they kind of go on and off. This is one by Durauto that's just been submitted. And this is another one found by my student here. You can see this one has been on consistently. So what can be it? And so some of the suggestions in here are magnetars. These are really magnetized neutron stars, like 10 to the 14 gas fields, because they tend to break very fast and you've got a lot more energy. So they could be maybe that's the answer. But I think the actual answer is going to be these are all white dwarf binaries. And what you're seeing is kind of a polar model. So you have a white dwarf that has a mega gas field, and then you have a companion that is a low mass star, say an M dwarf, because you need something to live a long time, longer than the G dwarf or F star that made the white dwarf. And you have the Jupiter interaction happening again. And it's just now you've just changed Jupiter for a white dwarf, a planet with a star. And the physics all works out. You know, you have to explain how you make this stuff with coronas and without plasma. Where does the plasma come? But you could potentially be measuring the magnetic field of a white dwarf at kiloparsecs. And it's very hard to do any other way. So I think this is a kind of like AR SCO, if people are familiar with that terminology, or polars. Don't know. I'm telling you this is a solved answer based on a sample size of 2. There's only 6 known so far, and we're just entering a new parameter space. But if people have ideas, I'm very happy to chat. So maybe what I should do, conscious of time, I should begin to wrap up. And so what am I doing right now? So we just, because LOFAR is undergoing this upgrade to LOFAR 2, we've submitted about 1,500s to hunt this periodicity on a large program, and that's currently under review. The idea of trying to find this pulsation is actually complicated, you know, because RVs are very different. RVs, you've got this on and off. I mean, you've got this blue shift and red shift, right? If you take a measurement of RVs of a star, you always get a number. But this is an on-off sequence. And so there's some subtlety in the way to do the periodicity search you need to think about, because the maser, that thing that's causing emission, also is time variable. And so it could be on and pointed at you, but it's below your sensitivity limit. So how do you account for that in your search algorithms without getting more and more data is a subtlety, and I think Gaussian processors have got the answer there. But if you've got ideas about it, I'm very happy to hear. We've also got TESS and LOFAR proposal coming up. So the idea is co-observe with TESS and see if there's any correlation with the optical flares in the radio. Measuring the magnetic field of the stars can really help with the inference of understanding what you're seeing, because it can tell you about the global structure of the star. What are LPTs and what are they super common? And then I'm going to finish on the SKA in the last minute or two before I finish. So I don't know if everyone knows, but the Germans are very close to joining the Square Kilometre Array Observatory. I think it's pretty much a done deal now. It hasn't been publicly announced, but I'm pretty sure it's all final stamps are happening at the government now. So maybe I thought, considering my position as Richard alluded to, I'm a head of the Square Kilometre Array Science group at ASTRON, and I'm one of the Dutch chairs of the council. I talk about this in 2 slides. So you can kind of see there's 2 telescopes here. One is probably what you expect, you know, a VLA on steroids in the south. This is going to be built in South Africa, in the Karoo. And there's one on the right, which is actually LOFAR on steroids. These are just kind of like Christmas tree dipoles. They're about a bit taller than me. There's going to be about 250,000 of those dipoles in the desert of Australia. And so just to give you some idea here, the headquarters is based in Manchester, but it's a multi-international effort. And when will it start? When would you be interested if you're a PhD student in the audience or a postdoc in the audience? In like 2 years, data will come in that will be, because luckily it's interferometer, so you can build out, that will be as sensitive as LOFAR, as sensitive to the VLA. So in 2 years, you can do cutting edge science with this instrument. And then obviously that keeps building. And then in 3 years, you'll be able to do the next generation type of science. So if you're a student or a postdoc in this audience, you should think about how your science, how SKA can help with that. And the frequency ranges are here. So SKA low being a low frequency thing is at 50 to 350 megahertz, and the SK mid being the gigahertz machine. So it goes about 350 to 15 gigahertz. So Photoplanetary disks are feasible here because you're more optically thin, and then kind of standard AGN physics, lots of stuff could be facilitated. And big win here is sensitivity, sensitivity, sensitivity. Okay, if you've fallen asleep, maybe I'll just leave you with 3 dot points, just the takeaways. I hope if you stand up and walk away, is that we're just getting the first detection of stellar systems at low frequencies. And it's unbiased view because we're doing this all sky survey. You're not just going targeting the active stars and just sitting on them. It's a new parameter space. And so far, all my arguments for the star-planet interaction scenario has been inference-based. But we've made a prediction, and that's what we're trying to test now, and that's hunting for that periodicity. And I think I'll leave it there. Thank you, Richard.
Thanks very much, Joe. It's really another exhilarating field. It's going to be great to see this all happen in the next years. I mean, we should all hang on. I'm going to ask the first question from Keys Dunnemont.
I have a question about the circular polarization fraction.
Yes.
You showed that for the stars, they are between 50 and 100%, right?
Yep.
I mean, it's really very strong. But if this is generated by the mechanisms that you are mentioning, wouldn't you get sort of a similar situation as with the AGN, that there are magnetic fields in all different directions and you will just kind of average it out? Why is it so high? I mean, it's just weird.
So the reason why, it's because essentially only one field line's doing all the work. This is heavily beamed emission, and it's quite high in the magnetosphere at the low frequencies. And so you're just seeing that one field line sweep across your eyes. That's the main reason. You're right, is in a sense that if all these field lines were active at the same time, I'd have the northern hemisphere and the southern hemisphere, and you average out. But in all these cases, you can just arrange the magnetosphere in such a way you've only got one field line doing the work. And that's just because of the beaming action of it, you know. And to get maybe a bit more subtle, not only is it beamed, it's actually beamed on the surface of a cone. And so you have this extra filtering on top of it. Does that make sense? Yeah. The question, a good question is, why isn't it all 100% circularly polarized? That I don't have a good answer for, because on physics thing, it's just it's all one-handedness. It's propagation out of the corona, I assume. You get Faraday rotation, you get all types of stuff. That's at least what observational astronomers write in our papers, like propagation effects. Full stop.
Another question from the room? Not at the moment. I don't see anything. Looking at the online audience, also nothing. If you want to put a question, please put your hand up or send a message. Oh, we have one. Yep.
Students are happy to ask me questions. There's no such thing as dumb questions.
Right. This may be dumb. On your last but one slide, you said something about fool's gold. And I think you didn't mention anything. And now I'm curious what that meant.
Oh, yeah. So, so this is another one. I didn't have time to go into it because I already felt like I was a bit errated. So this is the idea of correlation between the optical and the radio emission in terms of flares. And I had a student called Timo Yu who went through this with Harish and I. And you can do this on an ensemble argument. You go, what is the flare rate of a star and what is the radio detection of that? And you find there's not a strong correlation. And so the idea is maybe this doesn't exist, but we know on the sun there's a strong correlation between flares and radio emission. So that's why I got a question mark at the end, because there's at least one case on, I think it's Proxima Centauri, where we had contemporaneous optical and radio. This is not lo-fi work. This is ASCAP work by Andrew Zick, where you do see it. You see this giant flare and an impulsive radio emission immediately following. And so it does happen, but on an ensemble argument, we didn't see a strong correlation. So either we're doing something wrong or there's something more subtle going on.
Keys.
I was a bit surprised that you mentioned two mechanisms for the aurora borealis, both of which, but I always thought that it's one mechanism is just directly the solar wind just getting funneled by the magnetic fields onto the poles, but this is not among the two scenarios.
No, this scenario is exactly that. right? So what you do is you have an impedance of the solar wind, like a CME, hitting the Earth, and that actually suppresses the magnetosphere, and you have a reconnection event, what's called a Dungy cycle in the tail.
Yeah, but I mean, apparently, so what you're saying is the material from the solar wind gets in this closed loop here,
Yes.
and it's in the closed loop is being accelerated by the magnetic
So
connection.
you kind of snap. So imagine if so I'm trying to show on this picture, and it's not good. Maybe I can actually. I have the simulation. That's an obvious solution to this problem.
So maybe my question is there no direct particles that directly go from the sun straight onto the poles, or is it always this closed loop?
It always gets in this closed loop. Maybe there's. I'm not an absolute plasma expert in this. This is a question for plasma physicists. Yeah. But my understanding is all of it's being redone by the tail and accelerated back. Maybe there'll be some, but the majority of it's coming from the magnetospheric tail, because you need a current sheet set up, and that's where it gets done.
Interesting.
So it's called a Dungy cycle if you want to know more about it. D-U-N-G-Y or G-E-Y.
I'll ask myself a question if I may. I just wonder, just on a sort of hunch, I don't know enough about the physics of these M dwarfs, but did you look at the environment of the stars which you've detected? For example, we mentioned earlier on the idea that cloud-star interactions may lead to energetic phenomena.
So I haven't looked in the general environment. All I know is that not the low-far stars, but the ones we detect now with the higher frequency surveys, such as BLAS. Again, it doesn't really matter the names, but now there's an all-sky survey also going on with BLAS, and we've done some Stokes V parameter space with the BLA, sorry. Done some parameter space there. And what you find is a lot of them actually in young moving groups. I don't know if that's helpful for you to...
Sorry, a young what?
Young moving group, it's called. Essentially, it's like young open clusters and stuff. I don't know if they... I haven't done any parameter space in talking about clouds or anything like that. So I don't know the answer.
All right. Well, we still got time for questions. So please go ahead and ask. And while you're thinking, let me ask another question about the SKA.
Yeah.
You mentioned that... you maybe about one in 50, you actually have the transiting scene in an optical signature as well as you detecting these variabilities. What sort of numbers of these objects do you expect to see with STA? And also, what other classes of objects? For example, we know what the sun does. Can you see basically solar flare type flares on solar light types stars within a certain radius with SKA when it's fully operational?
Yeah, so I did those numbers in some of my paper, and you take the normative sensitivity they'll reach, and I think we will get about 10,000 M dwarfs with the SKA low if it does a survey like we've done with LOFAR. That's a big if, because I don't know if there's any radio astronomers in the room. It's confusion limited very quickly. In Stokes V, we're not. So it's because we wash out all the AGN, but will another person want to stare for 8 hours in the sky when you've integrated as much as you can in 2 minutes? You just hit the background after 2 minutes with SKA, because SKA low as it's built right now is mostly designed around pulsars and epoch reionization.
Okay.
Yeah. So that's why it's so confusion limited, if people are wondering.
We will have a lot of time for discussions later.
Yeah.
Is there any other questions here? No, but look, I just have to take the opportunity to ask you another question. Right, the pulsars. You mentioned that you have discovered pulsars.
Yeah.
Now, in certain environments, notably in the galactic center, it's extremely challenging to detect pulsars by traditional methods with dispersion. I mean, is there any hope that we are very, very highest angular resolution? I guess the answer is no.
Question. No, the answer is yes.
But are you going to be able to do something on that?
Yeah, well, unfortunately, the galactic center doesn't get very high at low far.
Well, look, it's going in the future is what I'm talking about.
People aren't familiar. Most pulsar searches are done by the fact that they pulse, right? And then what they have is very clear dispersion, because as radio photon goes through the ISM, the lower frequencies arrive later than the higher frequencies. And so that's how you search for these things. And some search algorithms, the classic ones, are biased in some ways. For example, millisecond searches, it's just really expensive to run the trials. And the other one is if it's highly scattered. And that's what happens when you're really far away or in a complicated environment like the galactic plane. And guess what? Most of the pulsars we found that weren't identified, they're highly scattered or they're millisecond pulsars, because that's where the pulsar astronomers aren't complete. Their search algorithms are trash. So that's where the galactic plane, the galactic center is very interesting in this parameter space. But maybe, I don't know. That's also like many pulsar astronomers have died on the hill of the galactic center. Because the reason why it's so interesting is because you can measure the dynamical structure and say what the galactic center is doing. You expect a lot there just based on stellar evolution.
So, Hans, question.
Thanks for your talk. I have a technical question. I remember since you were pointing to the rapid of efficient survey capabilities of LOFAR. I remember the very early times of LOFAR, and if I remember correctly, computer limitations were restricting, I think they could do 8 beams or so simultaneously.
Yes. Yep.
Is that still the case, or has that been overcome?
It's been largely overcome because of just computers become cheaper. So when the Dutch turned on LOFAR, which also had German stations and stuff, it was 2010, and it wasn't until 2015 we conquered a lot of those computational challenges of doing many facets and many beams. Even still now, actually, the bottleneck is actually with the beams is not actually the compute now, it's actually the fiber out of the telescope. We could make more, like the telescope allows us, so for people unfamiliar, beams kind of like a field of view of an optical telescope. And because we do software controlled, we can make lots of fields of view all over the sky. We just have to do something with the data. And that data comes out like a fire hose. And so the bottleneck is actually the fiber right now out of the site.
Okay.
And so we've got an application in with the Dutch government to just replace that fiber with 100 gigabit per second fiber. And that would allow us to do 8 simultaneous images over the sky.
Okay.
And LOFAR 2s in some way are going towards that. But yeah, that's a good question.
You.
And we still need more compute, by the way, and more storage. When I say that problem solved, I said like at least like computers exist, but we need more of them. And it's expensive.
Okay, well, I think we'll wrap up now. I see no more questions from the auditorium or online. Before we thank Joe, I'd just like to make some announcements.
I'll just get to the...
Yeah, okay, go to the next slide.
Yep.
That's just a... Yeah, so next week we're sort of oscillating in this series, right? We haven't decided whether we're going to be close by in the galaxy or, right at the edge. We're going right back to the edge of the universe. And these crazy, very high redshifts objects that nobody really understands. And we got the perfect person to tell us all about that. Jenny Green, she's visiting MPIA for all next week. Please get in touch with Nadine Neuhauptmeyer if you want to meet her, and do come to the colloquium. I think it's going to be an interesting one. The next one is tonight. We've got a dinner meeting. Everybody's invited. Please just come along to Damario. Maybe you can nudge me if you want to do so. Before that, however, we have some drinks still available, including some cool, non-alcoholic beer. Maybe if we stay long enough, some alcoholic beer as well next door. So maybe that will be, if you want to sort of linger at some of those additional questions of Joe that on processes that you were sort of alluding to.
And if students want to come to dinner, don't let money be a problem. I get a honorarium. I'm happy to pay for the students' dinner as well, if they want to come. So please, I'm just happy to chat.
This is the utopian guest we have here. Thank you very much. Well, let's now just thank Joe for that very interesting look into the future of astrophysics and radio astronomy and stellar physics. Thank you very much, Joe.
Thank you, guys.